Okay. In the previous video, we did the shear, and we're going to leave it on the page here. But now we're going to do the moment. Let's first deal with this section between 0 and 6. Basically, right in here. And if we look at that, we have something unique there, that is distributed load that sits there the whole way through. So I'm just going to look at an example here, just like we did before. Here's X. There's our 2875. What does our positive moment look like on the right? It looks like that. So we're just worried about the moment. Now there is a shear there, but I'm not going to draw it because I'm only interested in the moment. So what do when you're dealing with the moment equation? Sorry, excuse me. Yes, sum of the moments equal to 0. Now, just to show you that it doesn't matter, and that this direction that is assumed in this equation is independent of the direction here, I'm going to make them different. So I'm going to sum the moments about this point right here. 2875 x, because this thing is x apart, sum of the moments about here, I end up with that value. It is going in this direction, which is the same direction as that. Now, this load is 500x, if I remember right. Yep, 500x located at x over 2 over, going in that direction, minus 500x, that's the load, the moment arm, x over 2, and the only thing I got left is this. Now you notice it's going minus m. Move things around, what do you get? M is equal to, move this to that side of the equation, m is equal to 2875x minus 500x squared over 2. Let's take a look at this. First thing I want to look at is the relationship between this equation and that equation. If, just say, I decide to randomly do this, and I say, hey, wonder what would happen if I took a derivative of the moment with respect to x, I would get 2875 minus, okay, take derivative of x squared, it's just 2x. Well, the 2x would cancel the 2, and I'd get that value, which, not too surprising, is the same exact value as the shear. Just proving the point. of that. You don't have to know that for this test that we're talking about, but you might notice it. So now I'm going to make use of some type of plotting package, something to plot this. Since most people have seen Excel, I may use Excel. But I may also use MATLAB or something of that nature. But before we do that, let's make some observations here. I'm also going to change this. Say this is m as a function of x. Well, if I put in x equals 0, guess what I get? Moment of 0. Makes sense. This end of the beam is not cantilevered. That's the only way you can get a moment on the end, or you put a moment on the end. So, and then the question is, you could find out what the value is at anything between 0 and 6. So I think it might be instructive to just plot this. So I'm going to draw in MATLAB here. I'm going to do a clear the screen. I'm going to say x is equal to 0 all the way, say 0.1 all the way to 6. Then I'm going to move the thing down, and I'm going to say the moment is equal to 2875 times x minus 500 times x, and I have to put a period here because of the way MATLAB operates, divided by 2. Now I'm going to plot x in moment. Showed up on the other screen, so let me drag it back in here. So of course, one of the things we notice, just like we were talking about, starts at 0, comes up, kind of reaches a peak, starts declining here. Now, I'm going to slide this over, and I'm going to drag my thing right in there. Okay, so take a look at this. Right now, I am not concerned about anything to the right here, only up to here. You'll notice, you can't see it very well, but there's 8,200, and it's about that level up in here. If you want to, we can actually, MATLAB has a nice feature here that allows you to just zoom in on what you think the highest value might be, then use the hand to move yourself around. So you can see about 8265, and not too surprisingly, 8265.62. You want to get a little closer, you can do that. But it's still good. So move down to the next point. At 6, it's 8250. Is that what I've got? How about that? Looks to me like it's 8250. So I think we're good here. We have the moment in this equation, between 0 and 6. Now what happens? Well, what happens now is we need to deal with anything greater than 6. So we're dealing with the region. The next region we need to deal with is this region right here, because in there's no loads. that are added. And so we're going to basically deal between x equals 6 and x equals 9. Let's take a look at our beam. The beam itself, completely loaded. We'll just say this is 6 right here. This is our 2875. And we're going to say our moment here is a little bit different now. As we found out before, this is 500 times 6, or 3,000 pounds. Now we're at some new x value. As long as x is greater than 6, we've got to find this moment. Again, we do that moment equation. And I'll even go opposite again. And we're finding the moment about here. And what does that equal to? 2875x. And now what is this distance? Well, now it kind of depends. It looks as though this distance is important. Well, that is x minus 6. Okay, remember that. X minus 6. And then what is this distance? Okay, that's 3. So now, okay, you have to remember this is positive, this is a negative load. 3,000 times the moment arm. This moment arm. How about MA for moment arm? Well, that moment arm is nothing more than 3 plus x minus 6. Or you could say x minus 3. So we have one more moment to add, and that's a minus m. So now we get this equation that says this, 20, and I'm going to move this, the moment as a function of x, 2875x minus 3,000 times x minus 3. Am I wrong or right? I don't know. I'm a little bit worried, but I may be okay. Let's go ahead and simplify one more, and I'm a little bit scared I've messed up, but if I did, I'm not cutting it out of the video. I'm going to deal with it. Then minus and minus gives me a plus. 3 times 3 is 9. Or 9,000 minus 125x. Is that right? I think it is. As far as the math goes, as far as the actual answer, I have to check this out. Oh, remember when I didn't erase something? Now I can. So what I want to do is I want to say this is between x is equal to 6, wasn't it? Yeah, 6 to 9. Let's bring MATLAB back on the scene here. Gonna keep this plot. Keep it all good. Go over here and do a hold on. That holds the plot that's on there while I put the next plot on and make sure that I'm good there. So I'll do x in region 2 equaling to 6.1 all the way up to 9. And I'm going to do the moment in region 2 equal to 9,000 minus 125 times x. And then I'm going to do a plot. X in region 2, moment in region 2. Hopefully. Oh, I made a mistake here. That's supposed to be X in region 2. All right, let's take a look. Does that look right? Hey, let's check it out. Let's draw in our code right here. Looking good in one way. I think we're good. Looks like it dropped straight off linearly, and we'll come back to discuss that in a minute. But let's see what our values are. Okay, so what I'm going to do is, of course, I'll start at the start of the linear, which is 6 and 8250. Let's take a look and see if I can, pin this 6. I'm basically looking at the 6. I really don't see any bumping here. I mean, this looks pretty good. 8250. 8250. I'm pretty good. Let's go over to the other end, which is 9 at 7875. Let's see. 9, moment there, 7875. So in fact, you look across right here, you're at 9 and 7875, so we match that. Now, let's discuss this linearity here. Okay, first thing you notice is it was quadratic in one region, linear in another. Let's look at the shear during that region. Look at this. Interesting. The shear in this region is flat and or constant. The moment, linear. Shear in this region, linear. Moment in that region, quadratic. So in fact, this relationship is sort of holding here. Let's take a look. The derivative of the moment with respect to x in this region equals to minus 125. I'll be, look at that. There is your minus 125. So, in fact, again, that's the shear. Let's finish this up. Now, I know from looking at this diagram, the moment ends up at the very right end, equaling to 0. But let's go ahead and go through this. Okay, sorry about that. So x, in this case, we're going to look at is between this this 9 and the 12. So it's got to be between 9 and 12. So now the free body diagram looks, again, a little bit different. It looks like this. Goes out here. Goes across. This, of course, is 6. Suddenly there's a load here. I think it's 2,500. 2,500. This is 500 pounds per running foot. Again, here's our 2875. This is all the way out to x. This is 6. So now I can take this 6 off the top. This is 3. Only interested in the moment. So sum of the moments equals 0. And yeah, just to be consistently obnoxious, I'm going to make it go in the opposite direction. Now, what is that? Well, it's 2875 times x. Again, same logic. This one is 3,000 pounds right here at 3 over. Well, what is that distance? That is x and here's your problem. I don't know this distance, but I do know that x is going to be greater than 9, so therefore I'll say this is x minus 9. Say if it's 10, that'll be 1. If it's 11, that's going to be 2, so on and so forth. So this is that distance right here. So if I want to know the moment arm back to this 3,000 pounds, it's of course 3. Here. It's of course this 3, that 3, and then x by minus 9. So I'm going to kind of write all that. Now that 3,000 pounds is going in the opposite direction. 3,000 pounds times the moment arm of 3 plus x minus 9. Now I know that's a strange way of writing it, but it's okay. So the only other new load that gets put on here is minus 2,500 pounds, x minus 9, and then minus your moment. So you take this moment, you shove it back over to that side of the equation, and now you get the moment as a function of x equaling to 2875x minus 3,000 times, well, you take 6 right here, you pull off that, and you get x minus 3. Then you're doing this one, minus 2,500 times, you don't do anything there, that's just x minus 9. But you need to simplify all this, so you need 2875x minus 3,000x plus, 3 times 3 is 9,000, minus 2,500x, plus 9 times 2,500, well, that ends up being, okay, and that's a minus, and that's a minus, so it ends up being 22,500. So what you want to do is gather the terms with x's on them, and let's see what you get. You get, let's see, I'm going to go ahead and make sure 2875 minus 3,000 gives you your 125 minus 2,500 gives you your minus 2625 minus 2625x. Now do the terms without, and what you get is, hang on, you get 31,500. So your moment in that region is equal to this. Now let's go ahead and pick this up, see if we can resolve this in our trusty MATLAB code. Now I'm in region 3, so I'll say x region 3 is equal to, region 3 went from 9 to 12. And then moment 3, region 3, is equal to minus 2625 times x in region 3 plus 31,500. Hey, if I'm wrong, it's embarrassing, but you can't see me turn red. Okay, I hold on. I still think the plot's held on. Plot x3, moment 3. Now I got to find the plot. Uh-oh, looks funny looking, doesn't it? But that's probably because I had it zoomed way, way, way out. I mean, not way, way, way in, I'm sorry. So you take a look at this, and what do you see? First thing you should notice right off is, of course, at the right end of the beam, the moment drops to 0. And man, does it drop fast to 0. Is this consistent with our little web page? And if you look at it, sure is. Let's look at another thing here. Let's take a look and say, well, for fun, I'd like to take the derivative of the moment. Well, that's like minus 2625. All right, minus 2625. Hey, look at that. That is the shear. So I hope going through this problem has been instructive. I maybe have done a little bit more detail than I should have, but I'm hoping that you'll make ample use of this piece of software that is, of course, free. And, you can go back in here, and I believe, okay, so I believe, I've got this. This is the problem I just did. Okay, if there is a button, return to the calculator. Yes, keep the values. Okay, as I return to the calculator, let it kind of come up, I guess. Where did it all go? Okay, well, oh, it's back to this thing. Close. You see this, now I could go in and change something. I could move the point load, change its value. I can edit it. I can add a distributed load. I can do all sorts of things. So by all means, in your studying, don't hesitate to use something like this to sort of address the problem at that point. It would be quite advantageous to you to have something like this to verify as you study. On that makeup exam, this is the type of stuff very much that I'll expect, and I'll talk about that later. So this is the final video for this evening. This is December the 2nd, Wednesday, and you will soon receive an email.